folks. I guess we're back in our new reality, and we are going to do some online lessons just like when I had my surgery. So I guess it's good that I have a little bit of experience with this. And I'm going to pick up with some review from Chapter 9. We did start Chapter 9, but we really didn't finish up 9.1 and 9.2. And so, and I did more with one class than the other class, so I kind of wanted to backstep a little bit, do a little bit of 9.2, talk about how it relates to 9.1, and see if there's any questions on those problems. So, I'd like to take a look at it. This is on the handout from 9.2. I'm going to put all the handouts on Schoology for Chapter 9, including the homework list for Chapter 9, which I would ask for you to start working on 9.1 and 9.2 if you haven't already done so. This particular problem was about a basketball player who claimed that he shot 80% from the free throw line. So this is the problem I'm talking about. It looks like this. These notes are on Schoology all filled in as well. Okay, so want to go over the basics of a hypothesis test. And essentially what you're doing is you're making a claim and you're hoping to find a statistic that has a probability of occurring that's really, really small based on that assumption, that you can reject that assumption, because if what just happened is so unlikely, the assumption, the center of that normal curve, must not be correct, okay? So in this particular problem, he claimed that he shot 80% from the free throw line. And you always have equality in the null hypothesis. If we're trying to prove that he was exaggerating, we think that it's really below that value. So the alternative is going to be an inequality. A less than, a greater than, or in some cases a not equal to if it's a two-tailed test. I do have an example of the two-tailed test in these notes that's posted, but I would say I'm probably not going to do that on the video because I don't want to make these videos super long. Okay. So we've got our null hypothesis and the alternative, and we go through the following steps. So we know that we always have to test conditions if we want to use the normal curve, right? So we go through the same conditions, SRS, the independence, which is the 10%. And in this case, he has 50 tries. And so certainly a basketball player would make more than 500 attempts in a season. So we've got our usual first and second. These don't really change with confidence intervals or hypothesis tests. So this is, the last one is what's going to change. And so we need to look at the fact that, is this a normal distribution, right? So based on the assumption that P is 0.8, right? So this is the P in the null. I'm going to call that P naught. The large counts now is based on N times P naught. So large counts normality. So NP naught is 50 times 0.8, which is 40. That's certainly at least 10. And the NQ naught, which is 50 times 0.20, because the Q naught is just the complement of the P, 1 minus P. And so that's exactly 10. So we made it. So we could say that the normality condition is met. Okay. So we're always going to start off with the H naught and HA, or the ho and the ha. Some people call it that online. The conditions, and then here's where we're going to find the probability that the statistic occurred. So in this case, this basketball player, we know, shot 32 of the 50 that he tried. And so that p hat is 0.64. Oops. So what we're hoping to find is that the probability that he shoots 64% in a sample of 50, if it's really an 80% parameter that he shoots, for the most part, is if that's super small, then we've just found some evidence to reject the null hypothesis. So we make our normal curve. The null hypothesis is always the center. We put the statistic there, and then we need to figure out what the probability is of that statistic occurring at either that level or a more extreme level. Okay, so this right here, the shaded region, is the p-value. So the probability, and we're going to the left because it's a less than test, the probability that p hat is less than 0.64 is the p-value. So we're going to actually find the p-value on the graphing calculator, but what the graphing calculator is doing is it's getting the z-score, which is based on the p hat minus the p naught divided by the standard deviation. And then we're going to pick up our graphing calculator. So I don't think I did this in one of the classes. And I know a lot of people were absent that week, of course. So pick up your graphing calculator, please, while I let my dog out. So in the graphing calculator, you're going to go to stat, and then you're going to arrow over to tests. And you're going to see the one prop z-test, which is number 5. So it's asking you what's the p and the null, so we would put in the 0.8. And then it's asking you for an x and an n. So you're never going to enter in the p hat as a decimal. You're always going to put in the number of successes over the number of trials for that binary type event. And then you're going to select what the test is. Is it a not equal to, is it a less than, or is it a greater than? So this is a less than, so you toggle over, and then just arrow down to calculate. All right, so this is what I have on my graphing calculator. And then if I hit enter, notice what we see here, folks, right? We see everything we need. We see the z, which is negative 2.83, and we see the next p down, the next value down is the probability that p hat is less than 0.64, which is really, really small. Okay, so that was 2.83, and I mean, we could plug those in there, but really what we're looking for is the p-value, because this is going to help us make a decision. So when you have a hypothesis test, you usually start off with what I like to call a limbo stick, in terms of how much evidence do you need, what probability do you have to be below to be able to say that this is so unlikely that the assumption of the center of the curve can't be right, right? That if this occurred when this is true, this is probably not true. And by this, I mean the null hypothesis, the assumption for the whole problem. So then you're going to want to make your conclusion, right? And your conclusion is going to be threefold. Okay, the conclusion is going to state the p-value, all right, and I do have it in my notes on Schoology. It's going to make a comparison. So I would say, since 0.0023 is less than whatever alpha level was set, it's usually 0.05. Since 0.0023 is less than 0.05, we can reject H naught. Therefore, we have sufficient evidence to say that the true proportion of shots made is less than 0.80. So if you can reject this, then you can accept the null. If it's not below the bar set, the alpha level, then you would say failed to reject the null. You're never going to accept the null hypothesis because it's an assumption. You can't accept what you're assuming. You can reject it, but you can never accept it, okay? So you have three parts in the conclusion, right? You make the comparison. 0.0023 is less than 0.05. It should say alpha equals on top here. Therefore, we reject the null hypothesis. That's number 2. And then number 3, what does that mean? That means we have evidence to support that the true proportion is less than 0.80. And those are the basics of a hypothesis test. Okay? When you look at hypothesis testing, another big concept would be the types of errors that can occur. And I did start to talk about this before we left on March 12th that week, but again, many of you were absent. So type 1, type 2 errors, I did have this in the notes that I put on Schoology. I just want to kind of briefly go over that before I wrap it up here. Okay, so type 1 and type 2 errors. Type 1 error is easy because a type 1 error is that I rejected the null when the null is in fact true. So some people like to make the chart. So I reject the null or I fail to reject the null. And it's a mistake, right, if HO is true. So two things can happen, either HO is true or HA is true. And I never say HO, but I guess I've been watching too many videos to see if I could just put on a link for a video for you folks, and I decided just to make my own. A lot of people just say HO. I say H naught, usually. So if I reject H naught when H naught is true, then I've made a type 1 error. Okay, well that probability is really easy to calculate because a type 1 error, right? So let's assume we're doing the basketball problem, which we've talked about so much over the past few lessons here. So the probability that I reject it is going to be basically whatever we set as that alpha level. Okay, if we say that it has to happen less than 5% of the time, the p-hat's going to land to the left of that marker 5% of the time. Okay, so the probability of a type 1 error is just alpha. Okay. Now, you can make that error. You could reject it when it's true. Or, what if you landed over here so that the probability is greater than 0.05, but really the alternative was true? So, if that's the case, right, if you failed to reject it when the alternative is true, you've made a type 2 error. Okay, so a type 2 error, I'm going to make another normal curve, right? It's going to look the same, it's just going to be shifted over. Would have to be based on one particular alternative. So let's say the alternative is that, I don't know, he really shoots 0.7%, right, 70% of the time. In that case, right, you're going to be able to figure out the probability of making that mistake. because you would have this particular truth, right? And you would know where that marker would land for rejecting or not. And you really don't need to know how to calculate the probability of a type 2 error. You just need to know how to control it. So controlling a type 1 error is easy, right? If it's a bad thing that happens with a type 1 error, so think about what that would mean for the basketball player. You are rejecting H naught when it's true. So you think he's not very good, but he really is pretty good. He shoots 80%. That's good, right? So what would that do? Well, that's going to cause me to maybe not hire him back. I don't know if this is the NBA. Someday the NBA will play again, I promise you. But, you know, is that worse than a type 2? So think about what a type 2 error is here. A type 2 error would mean that I failed to reject this, even though the alternative is true. So he is he's not a very good player, right? The alternative is true, but I think he's pretty good. So from my perspective, you know, that would be pretty bad because I'm going to pay him the big bucks, but I'm not going to get my money's worth. We're not going to win as much. So depending on how the type 1 error works, right, you could do one of two things to make this blue area smaller, right? I could either slide this way, that would make the blue area smaller and the purple area larger. So that means I could increase alpha, and that would decrease the blue area, which we're going to call beta. And beta is the probability of a type 2 error. So they're really inversely related. So if a type 2 is worse, I'm going to increase alpha. But if I don't want to increase alpha, there's one other thing I could do. If I wanted to pull this curve in, right, that would decrease the standard deviation, I could increase the sample size. So if a type 2 error is worse, then what I would do is increase alpha or increase the sample size. That's going to make this area here, this 1 minus beta, even bigger. And we call this 1 minus beta the power of the test. Okay. You might want to look at a couple of YouTubes on power. It's not a huge topic. It's one that they'll sometimes ask in a multi-part open response. So if they're going to do open response, you might want to look at that and just look at the idea of controlling those probabilities. So if a type 1 error is worse for everyone involved, then you would decrease alpha, but decreasing alpha is going to increase the probability of a type 2 error. Okay. Now this is usually something that I spend a while on in school. It is a tough topic, so please look at that in 9-1 and come and ask me some questions this week. Okay. I'll have a couple of times posted for Zoom meetings. All right. Take care of yourself. Stay safe.